In this last chapter, chapter 33, we will very briefly touch upon the area of physics known as particle physics. Let's start with what are known as Yukawa particles. Yukawa was a Japanese physicist who worked in early 20th century. So Yukawa had a groundbreaking insight into fundamental interactions in 1934, like how do things interact, the gravitational force, the electric force, how do those interactions come about? Now, we are familiar with the idea of fields, which we have used to discuss electric forces, magnetic forces, gravitational forces. So we talk about electric field, magnetic field, gravitational field in order to discuss these forces. In 1934, Yukawa was working on the nature of strong nuclear force, the nuclear force that exists inside the nucleus, the attractive force which holds the nucleus together by balancing or actually overwhelming the Coulomb repulsion. So Yukawa was studying that strong nuclear force. And he had this insight that forces are perhaps transmitted through exchange of particles, through exchange. So when a proton exerts a force on an electron, they're exchanging a particle. And that's how the force is carried from one to the other. That's how one knows about the presence of the other. These particles that transmit a force or interaction are called carrier particles. Specifically for strong force, Yukawa proposed a new particle, which is now called a pion. And he proposed that this particle is exchanged between nucleons. So between proton and neutron, neutron and neutron, proton and proton. And this is kind of a schematic of how this would work. So you have a proton and a neutron. The proton emits a pion. In this case, it's a positively charged pion. When the positive charge leaves the proton turns into a neutron. And then this pion, this positively charged pion, is traveling towards the neutron and is captured by the neutron. Once the neutron captures this pion, this neutron becomes a proton. Well, the charge of the pion is exactly the same as the charge of the proton. That's why you have a conservation of charge here. So there's a pion exchange between a neutron and a proton. Now, pion has a non-zero mass. It has a mass. In fact, it's one of the heavier particles known, which means for that brief period of time, when the pion has been emitted by the proton and it's still in air, it hasn't been captured by the neutron, for that period of time, conservation of mass energy is violated. So it's like you're creating mass out of nowhere. We know that it's okay for conservation of mass energy to be violated as long as it's for a very brief period of time, as given by Heisen's uncertainty principle. So as long as delta T lies within this inequality, and where delta E is the amount by which energy conservation is violated, as long as the product of these obeys this inequality, it's okay to violate conservation of energy. So this inequality limits the distance that pions are allowed to travel, because they can be out in the open for a very short period of time, so they can't travel long distances. Otherwise, you're breaking conservation of energy. And that's the reason why a strong force has a very short range. The distance that the pions can travel without causing any problems with conservation of energy is of the order of speed of light times the time for which they are traveling from the proton to the neutron. Larger the mass of the carrier particle, shorter is the range of force. So meaning that if the mass of the carrier particle is bigger, it can be out in the open for a shorter period of time because it can only travel a shorter distance. Pion cannot exist independently, which means you cannot directly observe pions. Otherwise, you'd be causing a permanent violation of energy conservation. Such particles like pions, which could possibly lead to conservation of energy violation, are called virtual particles. They can't be directly observed, but their effects can be. There's an interesting calculation in the book, which we will go over. So taking the range of the strong nuclear force to be about 1 Fermi, about the size of the nucleus, or 10 to the negative 15 meters, calculate the approximate mass of the pion carrying the force, assuming it moves at nearly the speed of light. So here's how you're gonna do this calculation. The distance the pion travels, as I indicated earlier, is approximately speed of light times the time for which pion is allowed to exist without violating conservation of energy in accordance with uncertainty principle. So delta T is D over C. D is the distance it can travel, so it has to be within the nucleus, so about 1 Fermi and the speed of light. And this ratio is 3.3 times 10 to the negative 24 seconds. So pions, this virtual particle, is allowed to exist only for this period of time. Or it has this time for it to travel from the proton to the neutron or any other nucleons. Now, if you solve Heisenberg's uncertainty principle for delta E using this as delta T, you get delta T. Delta E is of the order of h over 4 pi delta T, and you plug in the Planck's constant and the value of delta T that we got here, and you solve this and convert the energy to MeVs by multiplying with the 1.6 times 10 to the negative 11. This calculation would have given you value in joules, but now you're trying to convert it to MeVs. So anyway, delta E comes out to be of the order of 100 MeVs. So that's the amount by which energy can be non-conserved within the nucleus. What does that mean for the mass of the pion? Now, mass is related to energy by delta E equals mc squared. So the mass of the pion has to be about 100 MeV per c squared. And this is about 200 times the mass of an electron and about 1/10 the mass of a proton or a neutron. At the time when Yukawa proposed the existence of this, no such particles were known. So it was quite a groundbreaking idea, which later on turned out to be accurate. Since then, their existence have been verified by colliding high energy beams of particles with nuclei. So basically by shooting high energy beams at nuclei, you're providing energy from the outside. And this input energy allows for the quote unquote creation of pions without any violation. So you're putting in energy from the outside, so they're not bound by uncertainty principle anymore. And in these experiments where high energy beams are targeted at nuclei, three types of pions have been discovered: a positively charged pion, a negatively, and then one which is electrically neutral. And the mass of these pions that were observed in those particle accelerators are of the same order of what the calculation, the 100 MeV per C square calculation that we did. So that verified that what Yukawa was talking about is actually accurate. It corresponds to the reality. The last topic we are going to look at is the four basic forces that we have learned about. These are the four basic forces: the gravitational force, the electromagnetic force, weak force, and strong force. The next column compares the relative strength of these. So if you take strong force to be of strength 1, then weak force has a strength of 10 to the negative 13. Electromagnetic force, 10 to the negative 2, and the gravitational force, 10 to the negative 38. So the gravitational force is extremely weak as compared to the other forces. I don't know if you remember the gravitational constant that we used in mechanics when studying the gravitational force. The value of the gravitational constant was extremely small when you compared it to the constant we came across in Coulomb's law, the Coulomb constant. So if you compare the gravitational constant and the Coulomb constant, you see the reason why the gravitational force is so much weaker than the electromagnetic force, and they're both quite a bit weaker than the strong force. Okay, and then the range of these forces. Gravitational force can act between masses that are at extreme large distances from each other. So we can say that the range of the gravitational force approaches infinity. Same thing about electromagnetic force. The weak force only extends up to 10 to the negative 18 meters, and the strong force 10 to the negative 15 meters. Weak force, you will recall, is what was responsible for beta decay. And then strong force is what's responsible for keeping the nuclei together by overcoming the Coulomb repulsion. These are the charges or the sign of the charges. The gravitational force is only attractive, so there's only one type of gravitational mass. You can have positive or negative electromagnetic, positive or negative weak, and positive or negative strong forces. The carrier particle for these forces, for the gravitational force, it's proposed that the carrier particle is called graviton. This hasn't been identified in real life, but that's the proposal. Electromagnetic force, the carrier particle or the exchange particle, is a photon, the particle associated with electromagnetic radiation. So electric charges interact with each other by exchanging photons. And this has been experimentally verified. The carrier particles for the weak force are 3, W plus, W minus, and Z naught. And these also have been experimentally observed. And finally, the strong force is transmitted by exchange of what are called gluons. And this is also conjecture at this point. So this is how, for example, the electromagnetic force comes about. The two positive charges here are exchanging a photon. And as it goes from here to here, it gives rise to a repulsive force. The first image shows the exchange of a virtual photon, the carrier particle, transmitting the electromagnetic force between charges, just as virtual pion exchange carries the strong nuclear force between nucleons. The second image shows that the photon cannot be directly observed in its passage. So remember, in this role of transmitting electromagnetic force, the photon behaves or is a virtual particle, it's a carrier particle. So you cannot directly observe it while it is going from one charge to another. Otherwise, you would disrupt this passage and you will alter the force. So each of the carrier particles shown in that table is a virtual particle, and you cannot directly observe while it's transmitting a force. Feynman diagrams are an extremely powerful tool for doing a lot of higher level particle physics involving fields and particles and virtual particles and so forth. So I'm just going to give you a flavor of what a Feynman diagram looks like. So here, what you see is two positive charges. So on the y-axis, you have time. On the x-axis, you have space. So time is flowing in the upward direction. So you have two protons which are interacting by exchanging a virtual photon. And this gives rise to a force of repulsion. So they're going to be moving away from each other. So that's the Feynman diagram for the exchange of a virtual photon between two positive charges. Time is graphed vertically while the distance is graphed horizontally. The two positive charges are seen to be repelled by the photon exchange. Okay, and then the last point, all carrier particles are fundamental, meaning they don't have any substructure. They're not made up of any tinier particles. Pions do have a structure, and they're made of particles known as gluons. Also, one property that all carrier particles have is that they're all bosons. You might recall we introduced the term fermions. Fermions are the particles that obey Pauli exclusion principle, and they are particles that have a spin, which is a multiple of 1/2. So either 3/2 or 1/2 or 5/2, etc. Bosons, on the other hand, are particles that have a whole integer spin, 1, 2, 3, etc. So all carrier particles are bosons. Okay, that is the end of this. That's the end of all we need to know in this chapter.